Mr. Bina here and welcome to Concept Map Lessons. And in today's episode, we will be talking about waves. So, what are waves? Here is an example of a wave. This type of wave is called a transverse wave. There are several types of waves though. We have the compressional wave, and similar to this transverse wave is a standing wave. We will discover all of these waves in the next slides. Basically, waves is actually a transfer of energy from one place to another. Waves can be also called a traveling disturbance. So, this is an illustration of a wave. It really is a disturbance in space. It is moving upward and downward while traveling in a forward direction. This type of wave is called a transverse wave. Waves, also known as traveling disturbance, can move through matter or a medium, or another type of wave can also travel in space and it doesn't require a medium or a media. Literally, the compressed wave or compression wave will only travel in a medium or matter, while transverse waves can travel in space. Here are two types of waves. The first wave on top is actually called the compression wave. This compression wave is actually compressing, in this case, air as the medium. So it compresses air so that it can travel from the speaker to the ear. Basically, this is a type of sound wave, and sound wave is a type of a compression wave. Below is a type of a transverse wave. Unlike the compression wave, the transverse wave will travel up and down and moving in a forward direction. That is how energy is transmitted through a transverse wave. A transverse wave is a type of wave that can travel in space, meaning it doesn't require a medium to do that. An electromagnetic radiation such as gamma ray, so this is a much higher frequency wave, X-ray, ultraviolet, visible light, infrared, microwave, and radio waves are literally a type of a transverse wave. And transverse waves, such as these types of waves, doesn't require a medium or matter, such as air or water, for the waves to travel. So this is how the radiation of the sun, a type of transverse wave, can reach into the surface of the earth by just traveling simply through space. So we will now try to discover the different types of waves that I mentioned already earlier in this slide. Again, there are two types of basic waves. The first one is a transverse wave and the other one is called a longitudinal wave, also known as a compression wave. So we will first look at what a transverse wave is. So if you look at the diagram of how the transverse wave is propagated, and we are going to make a horizontal line, let us consider this line as the equilibrium line, and so the displacement of this transverse wave is going up and going down. So basically, if we connect one part of this wave and the other part of this wave, it can actually create one circle. And this is the reason why that half of that circle and another half of that circle can create one cycle. And this cycle or this shape is also known as sinusoidal shape. Now what about the longitudinal wave? So this time we will look at the anatomy of a longitudinal wave. Now here is an illustration from the internet of how a compressional wave looks like. And if we look at the diagram of a compressional or longitudinal wave, this type of wave in here, because they are compressed to each other, so this is the compression region of that wave. And in the other section of the continuum of this wave is a little bit lax, and we call this the rarefaction, meaning to say not the compression. So another sequence will be another compression. Now from the middle of one compressional wave to another compressional wave, that is our what we call the wavelength. So basically this compression wave and another compression wave is called one cycle. And another rarefaction to another rarefaction can also be called a wavelength or one cycle. So what are the different elements or different parts of a wave? In understanding the different parts of waves, we will consider in here the transverse wave. First is what we call the trough. The trough is actually the lowest part of a wave. Now, this is an example of a transverse wave, and this is the neutral or the neutral horizontal line, and the lowest section of such wave is called a trough. This is another wave trough. Now opposite to the trough is called a crest. The crest is actually the highest part of a wave. That is why the crest is the opposite of the trough. So earlier, this red dot is situated in the trough. Now, this red dot is situated in the wave crest. Again, the wave crest is actually the highest section of a wave, transverse wave. Now, next one is the wave height. Now, from the neutral line, going to the wave crest is called an amplitude. From the neutral line, going to the trough is also called an amplitude. The summation of two amplitude, meaning from the wave trough to the wave crest, is called the wave height. The wave height is actually the vertical distance between the wave trough and the wave crest. So I am illustrating this again. This is the wave trough and this is the wave crest. The vertical line, that is the summation of the two amplitude from the neutral line to the wave crest, and from the neutral line to the wave trough is called the wave height. Now what is the wavelength? The wavelength is the distance between two consecutive wave crests or between two consecutive wave troughs. So actually the wavelength is actually the exact cycle of a wave. So here is the illustrative version of a wavelength. Again, the wavelength can be measured from a wave trough to another wave trough, or from a wave crest to another wave crest, which create one cycle. Next is the propagation of the wave. When we speak of propagation, this is actually the movement or the activity of a wave. So the movement or the spreading of such wave. And the direction of the wave propagation is always going away from the source of the propagation of the wave. Look at carefully the source of this wave. Again, this is literally a transverse wave, and the wavelength is also traveling along the propagation direction of the transverse wave. So all of the conditions of the propagation of waves is true to both longitudinal wave and transverse wave. Let us examine first what a longitudinal wave is, or what is the nature of a longitudinal wave and what are its examples. Now here are two springs. Usually, we can create the two types of waves using the springs. If we shake the first spring on top in a sideward direction, we can create this transverse wave, meaning the transverse wave will be moving up and down and into the propagation direction. But if you look at the other type of wave, such as this longitudinal wave, this is a type of wave wherein the source of the wave is just pushing in the longitudinal direction. And so you see that the compression wave is traveling along the longitudinal section of the spring, while the rest will experience the rarefaction of this type of wave. So again, longitudinal waves can also be known as compressional waves. And so look at the difference again between the longitudinal wave from a transverse wave. Longitudinal waves vibrate parallel to the direction of the propagation. Look at the illustration again for the third time. An example to a longitudinal wave is sound or sound wave. So this is a sound wave. So sound wave occur when air molecules will hit another air molecule so that they will have to create the wave pattern and travel into the direction of the propagation. So this is the illustrative version of that explanation, as the diaphragm of this speaker will create a vibration into the air. The air will detect the movement of the diaphragm, and so it will create a certain pattern of a compression and a rarefaction and a compression of the waves. Thus, will create a different types of frequency and therefore will also develop or create the vibration called sound. Since it is a longitudinal wave, such as the sound, it will really require a medium. A medium is where it will produce the wave, where the wave can travel into. An example to this are air, metal, and water. You cannot produce a sound in space. That's why astronauts can communicate with each other using a radio wave. Radio wave is a type of a transverse wave. It can travel through space. While inside their astronaut suit, it has an air and an atmosphere. So that radio wave is translated into a sound wave. However, sound wave can travel through air. It can also travel to water, and also it can travel to solid objects such as metal pipes. Now let's move on to transverse wave. As mentioned several times, transverse wave can travel through space such as light and the heat of the sun as irradiation. Transverse wave can vibrate. Another name for vibrate is oscillate or oscillation. They oscillate up and down. They oscillate up and down about their individual equilibrium positions, such as going up to the crest and going down to the trough, as the wave passes by it into the direction of the propagation. Now, this is the illustrative example of the transverse wave that moves up and down through their equilibrium line. So all of the movement going up is called the amplitude going to the crest, and all of the movement going down from the equilibrium line is also called an amplitude that is going to the trough. And the direction of the propagation or the oscillation of this transverse wave is always opposite to the source of the wave. Now, an example to transverse wave or the moving of up and down direction type of wave is a water wave. Our ocean is creating waves no matter how irregular the waves are, but they obviously create the up and down type of wave. Another example of the transverse wave includes electromagnetic wave. An example to an electromagnetic wave is light wave. Now, if we examine the type of light wave, it is only a very small fraction of the electromagnetic spectrum. Now, as the wave is going to the left, the more it increases its frequency, meaning to say the oscillation becomes too many in every fraction of a second, while as the wave moves towards the left towards the right, the more the wave becomes spread and the more that there will be only few oscillations of this type of wave in a fraction of a second. And it so happened that the visible light is belonging to this section of the electromagnetic spectrum. So meaning to say, it is a light, it is a type of transverse wave, it can travel into space. Now there is a way to calculate the speed of our transverse wave. The speed of a transverse wave can actually be calculated by the expression velocity v is equal to lambda times f, which is the frequency, and lambda here is the wavelength. Here is another illustration to that one. V is actually the wave speed in meters per second, and that will be equated to the frequency that is given by the unit hertz, or the number of oscillations in every second that will be multiplied to the wavelength that is given by the unit meter. Although some of the waves are very small, that is really small, up to micrometer, but we are given the unit of meter as a standard measurement for our wave speed. Now, for example, in this problem, what is the wave speed if a string, for example, has a frequency of 50 Hz? So imagine a string is being plucked, such as the string of a guitar. So when this is plucked, it will create a type of transverse wave that is having a 50 Hz, or meaning to say that there are 50 oscillations within 1 second, and a wave distance from one crest to another crest, or from one trough to another trough, that is given by the symbol lambda, that is equal to 20 centimeters. So the formula again for finding the speed of the wave is given by the formula v is equal to frequency times lambda, and then the solution will be just to simply change our variables into the given values. So v now is equal to the frequency, which is 50 Hz, multiplied to 20 centimeters, and that becomes 50 times 0.2 if we convert 20 centimeters into meter, and that will be only equivalent to 10 meters per second. That is the speed of that string that is being plucked. So again, let us recognize that v is actually the speed of the wave in meters per second. F is the frequency of the wave in hertz, and lambda is the wavelength in meters. And again, speed is equal to wavelength times frequency. So going back to the concept of speed of a transverse wave, we can also look at it in this manner. The concept of period. Actually, period is equal to the opposite of frequency or the reciprocal of frequency. In other words, period is equal to 1 over f. Why is there such thing as period? Because period basically is the number of time that is required for every oscillation or every cycle. That is why period is the opposite to frequency. And wave period is also associated with wavelength and velocity, so that our wave period, which is t, is equal to lambda over v, and we can also calculate v using period instead of frequency. Now problem 2 is giving us another problem that will be utilizing period to illustrate our point. Now what is the period of a radio station of frequency 801 kHz? Meaning 801 times 1000. That's the number of oscillations in every second. And the formula for period is actually opposite to the frequency, and the solution is that period is equal to the opposite of the frequency, that is equal to 1 over 801 kHz. And the answer is 0.0012, that is the number of time per cycle, or 0.0012 second per cycle. So again, period is indirectly proportional to the frequency of the wave. In other words, period is just the opposite of the frequency. So by the way, we can also relate period with velocity. Now let's move on to phase vibration. What is phase vibration? An example to this is that if there are two sound waves of the same frequency that are perfectly aligned or superimposable, they will have a phase difference of 0. For example, this is a transverse wave. If they are superimposable or aligned, all of their wave crests and their wave troughs and even their wavelengths are aligned. Now, to give you a better understanding what is an in-phase wave and what is an out-of-phase wave. So here we have one particular transverse wave. It starts from 0 degrees, and the first half of the circle will be up to 180 degrees, and the other half of the circle will be the opposite of the crest, which is going to the trough. This is from 180 degrees to 360 degrees. In other words, this 2 is already making a one complete, this one, the 2 is already making one complete circle. So this is the first semicircle, this is the second semicircle. So we can erase that, we can also erase that. Alright, now we will illustrate the difference between an in-phase wave from an out-of-phase wave. Supposing there is another wave that has similar amplitude, and it also starts from 0 degrees, and that wave will follow the same path. That's the crest also of the second wave, and it will also go back to the equilibrium line, the same as the original wave, and it continues and also creates its what we call a trough and follow the same direction of the original wave. And so this type of wave is called an in-phase wave. An in-phase wave is also known as a constructive wave. Why? Because the two amplitudes are aligned and the summation of the two amplitudes, such as the two crests and the two troughs, will create a much bigger or higher amplitude than the original waves. And now, in-phase vibration or in-phase wave. This is another illustration of an in-phase wave. There are two waves, identical, and they both start from zero. So it is not out of phase but rather an in-phase wave. An in-phase wave or constructive wave will create an amplitude that is much higher than the two original waves. In-phase wave will produce a sound, for example, a sound wave, with an amplitude equal to the sum of the amplitudes of the two waves. This is already illustrated earlier. This is also known as constructive interference. So again, when they are in phase wave, they will produce a much bigger amplitude compared to the original two, and this is called a constructive interference. This in-phase wave is the exact opposite to out-of-phase wave. An example of out-of-phase wave is if the crest of one wave and the trough of the other wave pass at the same time. This phenomenon is called out of phase by 180 degrees. So we will start with the 180 degrees. For example, we'll use the color blue to illustrate the second wave that will cause the out of phase. So we'll start from 180 degrees. It is very identical to the first wave. However, this is creating an exact opposite to the original wave. And you can see that while the original wave is producing its trough, the wave that is imposed in here is producing its crest. So that can continue farther. Now, if you notice that this amplitude will cancel out this amplitude, and later on will produce what we call a flat line. So this is also called a destructive wave. Since it starts from 180 degrees, the exact opposite of the original wave, this is called 180 degrees out of phase. This is another illustration that describes the 180 degrees out of phase. Out of phase wave. The out of phase wave can result by summing the two waves or adding the two waves that are opposite to each other, and usually result in a much smaller amplitude compared to the two original existing waves. And sometimes, if the two waves are identical to each other, they produce a flat line also known as zero. That is why the out of phase wave is also called a destructive interference. Why destructive? Because they are 180 out of phase and each amplitude will cancel out each other. So this wave A and wave B will be added, will produce a flat line or zero. That is what is meant by a destructive wave. However, this phenomenon is applied in noise-canceling technology such as headphones. In my case, I am recording this PowerPoint presentation for you In a relatively noisy environment, there are motorcycles outside, dogs barking, and sometimes people shout. But because of the headphone that I'm using, the headphone will actually copy or record the noise outside and producing the similar wave and creating an out-of-phase wave of the original wave. And that's how noise cancellation technology is developed. And so literally, you can mostly hear my voice rather than the noise created outside. Now, let's go to the concept of standing wave. This is what a standing wave looks like. It has a node and an antinode. Both ends are fixed. That is why another name for standing wave is a stationary wave. A standing wave. An example to this is the plucking of a guitar. Now this is a plucking of a guitar. Now you notice this string, it is now creating a standing wave. A plucking of the guitar will emit a particular sound frequency that is dependent on the string length and the density of the string. And this is what we call the notes. Now in this illustration, there is a vibrator and there is a string attached, and then the other end of the string is also attached to the wall. As the vibrator starts to vibrate, it oscillates the string. However, because the string is attached to the wall, it bounces back and creates one antinode, while the one that is at the minimum vibration is called the node. So this one antinode of one string is called the fundamental, given by the formula L, which is equal to 1/2 of the lambda. The lambda is actually the what we call the wavelength. Now let us examine the second illustration, letter B. It produces two antinodes. Now this is called the first overtone with the formula L that is equal to 2 times 1/2 of that lambda. Now if it produces three antinodes, the A, C, and E antinodes, then it is called the second overtone with the formula L is equal to 3 times 1/2 of the lambda. And finally, the third overtone is the consequence of creating the four antinodes. So this overtone actually will create the different types of frequency. Now for the next slide, we have an example using the formula in the previous slide. Supposing a string that is 2 meters long is driven by a vibrating motor, the same as in the illustration below, will have a frequency of 240 Hertz. 240 Hertz simply means there are 240 cycles in 1 second. The string resonates in 4 segments. 1, 2, 3, and 4. Now the question, what is the speed of the transverse waves of this string? This is the illustration of that string. Now the solution is, since there are 4 segments, L is equal to 4/2 times lambda, or 4 times 1/2 lambda, or that is also equal to, remember that 4/2 is 2. So if we calculate for lambda, then lambda is equal to L/2. And L/2, remember that our L is 2 meters long, divided by 2, that will become 1 meter. So our lambda is equal to 1 meter. That is the length of our wavelength. Now to solve for speed, we can make use of the formula lambda is equal to the speed times the period t. Remember that period is the opposite or reciprocal to our frequency. That is 1 over f. Now the solution is our lambda will be multiplied to v times t, which is 1 over f, is now equal to v, or solving for v is equal to the frequency times our lambda. And to solve for v, since we have the frequency, that is 240 cycles per second or 240 hertz multiplied by the lambda, which is only 1 meter. And therefore, our speed of the string is equal to 0.24 kilometers per second. So basically, this is now converted into kilometers per second. So again, the standing wave is produced whenever there are two waves of identical frequency that interfere with one another while traveling opposite direction along the same medium. Now, why do we say that they are traveling in the opposite direction? Because remember that when the standing wave is generated through a vibrator or a source of that wave, it is going to move away from the vibration or the source, going into the propagation direction, but it hits into the wall, while the source is continuously providing that vibration. There is always a supplemental amount of source that produces a wave, but again the wall will bounce back and then they will collide at the middle. So this collision will result into what we call a superimposed waves. And there are two scenarios here. The first scenario is that the wave can be added together. The addition of wave that creates the segment is called an antinode or antinodes. This is one segment, this is another segment, and the vibration of this segment is called the antinode, while the one that is just settling at the middle with a very minimal amount of vibration is called a node. So again, the antinode is the result from the constructive interference of the two waves and thus undergo a maximum displacement from the rest position or the equilibrium. Now, what is the other scenario of a superimposed wave in a stationary wave or a standing wave? That this possibility can also cancel out the wave. The flat line that is the result of the cancellation of this destructive wave is called a node. Again, this node is the result of the destructive type of waves that are added together. So basically, when we speak of nodes, these are actually the points of the standing wave of no displacement that is caused by the destructive interference of the two waves when they are added. And nodes seems to appear in a fixed position or fixed.